The title of this talk was disingenuous. It was called Life, the Universe, and Nothing. But now that the doors have been locked, this is the real title of the talk. And so I will explain to you precisely what I mean by that. It is in the evening, and some of you may nod off, so I thought I'd give the general content right at the beginning so you get the idea. By beginning with, I've given 2 commencement addresses myself, but I've never had the courage to say what this commencement speaker said at a private girls' school. Attributed perhaps to Kurt Vonnegut, but I'm not sure. He began his address by saying that things are going to get unimaginably worse, and they're never ever going to get better again. And so that's basically the content of this lecture, just so you know. We'll talk about that. So the summary of what I want to do is I want to explain why the universe we live in is probably the worst of all possible universes to live in. So much for intelligent design, in fact. It'll probably end badly, but it doesn't really matter because cosmology is going to end, as I'll show you. But I'm also a great optimist, so I want to point out that diamonds are forever, however. My mother would appreciate that, in fact. I used to live in Cleveland, as Ray pointed out, and then I'd always have to tell people that these are stars. And now in Arizona, I don't have to anymore. But they are stars, and for as long as people have been around, they've looked up at the night sky at these beautiful stars, and the sky seems static and eternal. And what we've learned in the last decade or two, with some of the things that are being discussed at this meeting, is that our picture of the universe has changed dramatically, perhaps more in the last decade than it had in the last century. And the implications are quite significant, as I'll describe to you. And one of the things we've learned is that as pretty as the stars are, the important stuff in the universe is the stuff between the stars, the stuff you can't see. And that not only determines the present universe, but will dramatically change the future, as you'll see. Now, scientists looked out at the night sky in the early 20th century, and it also looked static and eternal for them, and that was the conventional wisdom, in fact. The turn of the last century is that the universe was largely the same and had always been the same and would always be the same. And that was true at the time that Einstein developed his general theory of relativity, his greatest triumph. A theory that told us that not only how objects move through space, but how space itself moves. It was a theory of space and time. And therefore, in principle, the first theory of the universe. It was a beautiful theory. The problem is it didn't describe the universe the way it looked. Nowadays, that doesn't bother physicists so much, but it used to. And Einstein was very discouraged by the fact that he had this beautiful picture and it didn't describe the universe. Now, the problem was that the universe was static. And his theory didn't allow for a static universe. In fact, his theory suffered from the same problem that Newton's law of gravity suffers from. Namely, anyone who's taken physics knows that gravity sucks. Okay, it always pulls, it never pushes. So if you put a bunch of stars out there in the universe, then they will collapse together eventually because of their mutual gravitational attraction. And there's no way you can have a static universe. And the same was true with general relativity. And he was quite concerned about that, but he was able to fix it up. So I'll show you how. The doors have been locked now. These are Einstein's equations. And, but I tried to prepare them in a user-friendly fashion, so let me see. Okay. So we're all okay with this? The lawyers are okay? Good. Okay. It's not completely facetious because, in fact, in Einstein's equations, the stuff on the left-hand side refers to all the geometric aspects of space, because Einstein's general theory of relativity tells us that space, in fact, is dynamical. It responds to the presence of mass and energy by expanding, by contracting, by curving. And all the geometries on the left-hand side and the right-hand side is the stuff that makes it curve. So the curvature stuff on the left-hand side and the energy and momentum of the universe on the right-hand side. Okay, that's Einstein's equations. And since I'm a theoretical physicist, I have to write down the Greek letters. And there you go. It's much more illuminating now, right? Okay. Now, this was the picture that didn't describe the universe that we lived in, according to Einstein, because it didn't allow for a static universe. So he was a very creative guy, and he realized that consistent with all of the mathematics that had led him to general relativity, he could make a small change in the equations, and he could add an extra term to the left-hand side, which he called the cosmological term. And what it would do would produce a very small repulsive force throughout the universe, throughout all of empty space, so small that you'd never measure it here on Earth. You'd never notice it. It wouldn't destroy the beautiful Newton's descriptions of the motion of the planets around the sun. But it could build up. So on the scale of our galaxy or larger, it could hold apart distant objects against their gravitational attraction. And he hoped it would result in a static universe. Now, that picture was interesting, but Einstein later called it his biggest blunder because shortly after he developed that picture, we learned that the universe wasn't static. In fact, and in fact, one of my favorite humans, because he gives me great hope for humanity, is this guy here, Edwin Hubble. Edwin Hubble started life as a lawyer and then became an astronomer, so there is, in fact, hope for everyone. And he made several major discoveries. The one I'll talk about in a second, but maybe I should mention the first one because it gives you some perspective of really how nascent this whole field is. With the Mount Wilson telescope in 1925, he resolved a big problem. Up to that point, with telescopes that have been around, when you looked out in the night sky, you could see these fuzzy blobs through telescopes. Okay? They were called nebulae, which is Greek for fuzzy blob. And there was a big debate about what were they, and were they in our galaxy or not. In fact, in 1925, we knew of one galaxy in the universe, our Milky Way galaxy, the one we live in. That was the universe. But then with the Mount Wilson telescope, he was able to show that many of these nebulae were in fact other island universes, other galaxies. We now know there are 400 billion galaxies in the observable universe. Okay, in 1925, less than a lifetime ago, in fact, we knew of one. So we're really just at the cusp. Our picture of the universe is constantly changing, and that's one of the reasons why it's an exciting time. Now, how did he see that the universe was expanding? Well, he did the following. This is an image. These are galaxies. They're not sperm. Okay, and if this is our galaxy here, what happened when he looked out in all directions with the large telescope? Absolutely. When he looked out in all directions, that galaxies were moving away from us. Okay, and in fact, on average, and those that on average were twice as far away from us were moving twice as fast away from us. Those 3 times as far away, 3 times as fast, etc. So, what do you know from this? Well, this tells you obviously that we are the center of the universe. Okay? Certainly, that's what it looks like. But as my wife, who is here, reminds me on a daily basis, that in fact is not true. It really tells us that the universe is expanding uniformly. Now, I spent a long time trying to try different methods to explain why this is the case, and the real problem with this picture is that we're in it. Okay? The only way to really see that this describes an expanding universe is to get outside the universe. It's hard to get outside of our own universe here, for most of us, but we can do it by getting outside of the box in a 2-dimensional universe. So I've created a 2-dimensional universe here, which I've drawn with some galaxies, nice regular locations here. At one time, T1, and at a later time, T2, they're here. And you notice the whole system is expanded. The galaxies are further apart, and it's easy to see because you're standing outside of it. Okay. What would you see if you were stuck in this picture? Well, pick a galaxy, any galaxy, say that one. Okay. To see what you'd see, well, all I have to do is superimpose this picture on top of that one, putting that galaxy on top of itself to see what you'd see from that galaxy. And what you'd see is, of course, precisely what Hubble saw. That every galaxy is moving away from you, and those that are twice as far away have moved twice as the distance. At the same time, those that are 3 times as far away have moved 3 times as far. And it doesn't matter what galaxy you pick, any galaxy, you'll see exactly the same thing. So depending upon whether you're an optimist or pessimist, there either is no center of the universe or every place is the center of the universe. Okay? It doesn't matter. What Hubble saw told us, in fact, that the universe is expanding, and that changed everything. Because if the universe is expanding, that implied it had a beginning. In fact, we now know the beginning is about 13.7 billion years ago, except in Texas where I was recently. But in the real world, it's 13.7 billion years. And it had a beginning, and the big question then, of course, the central question of 20th century cosmology was, how will it end? And, well, before I get there, I want to just talk about poor old Einstein. So he had thrown in this cosmological constant, and he said it was his biggest blunder because you don't need it. If you have an expanding universe, then you don't need a repulsive force, because if the universe is expanding, gravity can be purely attractive, and it can work to slow the expansion. So if we're trying to really determine the future, in fact, the question is, how much gravity is there? Okay? because if there's enough gravity, it should be able to slow the expansion and cause it to recollapse, and that was the question. So he got rid of this term, but the problem is it's kind of like putting the toothpaste back in the tube. Once it's out, you can't get it back in. And if Einstein had not invented the cosmological term, someone else would have, because now we think of it in a very different way. Through the miracle of modern mathematics, one can rewrite this equation. Okay, it's a small step for a mathematician, but a giant leap for a physicist. Not necessarily to take that term and put it over there, but you see, when this term's over here, it suddenly has a different significance, because now it's on the right-hand side of the equation, and now it looks like an extra contribution to the energy and momentum of the universe. And you can ask, what would give such a contribution that would have produced a cosmological constant like Einstein? And the answer is absolutely nothing. But by that I mean nothing. Namely, not nothing, but nothing. Okay? Namely, if I take empty space and get rid of all the particles, all the dust, all the gas, all the light, all the photons, everything, if that empty space weighs something, then it will give such a term. Now, it's crazy for empty space to have energy, and so theoretical physicists like me knew that this had to be zero, right? And so we ignored this term for a long time. But if we want to know about the future of the universe, we have to know the energy of everything, including potentially the energy of nothing. So we have to weigh the universe to determine the future. Now, if we want to weigh the universe, as I say, this is a simplification, of course. Einstein tells us that space is curved in the presence of matter. If I have enough mass in the universe, it'll curve the universe and make it what's called closed. What does a closed universe mean? It means if I look out far enough in that direction, it means space is closed upon itself. So if I look far enough in that direction, then I'll see the back of my head. If I look really far out, then basically light will go around the universe and I'll see the back of my head. Okay, that's a closed universe. An open universe is spatially infinite. And here, obviously, it's pretty hard to draw a curved three-dimensional universe, but it's easy to draw curved two-dimensional spaces. So this is a closed two-dimensional surface of a sphere, an open universe, and the boundary between an open universe and a closed universe is what's called a flat universe, one where there's just enough matter to make space flat. And this is a two-dimensional flat universe. A three-dimensional flat universe is a three-dimensional analog of that. All that sounds great. That's the kind of stuff you talk about at cocktail parties. But really, that's really, like many things, it's irrelevant. The words are irrelevant. What matters is what's going to happen. And in a universe dominated by matter, if the universe is closed, the expansion of the universe will continue, one day stop, and the universe will recollapse in a big crunch, the reverse of the Big Bang. In an open universe full of matter, the universe will expand forever. And in a flat universe full of matter, just at the boundary between those two, the universe will expand forever, slowing down and never quite stopping. And so the question is, which universe did we live in? Because then we determine the future. And that's why I got interested in it, because I figured if I could figure out how much mass there was, I would know which universe we live in, and therefore the future. Now, there are many ways to nowadays, in fact, that was 25 years ago, 30 years ago almost. And since then, we've actually been able to weigh the universe in many different ways. And this is one way to weigh the universe. In fact, I could give a whole lecture on weighing the universe. But this is one of the most recent examples of being able to weigh the universe. This is a picture. It's one of many beautiful Hubble Space Telescope pictures. And it's a picture of a cluster of galaxies. Clusters of galaxies are the largest bound objects in the universe. They're millions of light years across, and they're basically the largest structures in the universe. And anything that can fall into anything will fall into a cluster of galaxies. So if we can weigh the cluster of galaxies, we in some sense can weigh the universe. And this picture is one of the ways of weighing this cluster of galaxies. Okay? Every spot in this picture is not a star, but a galaxy, first of all. Okay? Each of these galaxies has billions of stars in it, and civilizations that long ago may have died out. And this cluster is perhaps several billion light years away from us, but you notice in this picture there's something weird. You don't have to be a rocket scientist to notice there are weird blue things. What are those blue things? That's a phenomena that Einstein predicted in 1937, but he said it would never be observed because he underestimated observers, and that's easy to do. And he didn't think it would be possible. See, Einstein told us that space curves in the presence of matter. So if you have a big enough mass, then light from behind that mass will curve around it. Okay? And just like my glasses, that mass can act like a lens. My lens curves the light, and in the bottom in particular, it magnifies it so I can read. And if I had a cut glass goblet, for example, and you look through that, you'll see many different images in the room, okay, because the light gets bent many different ways. Well, matter can act like a lens, according to general relativity, and Einstein said it could, but he wouldn't expect to ever be able to see it. Well, this is a gravitational lens. Each one of these blue things is a different image of a single galaxy located several billion light years behind this cluster. All of them are different images. Some of them are magnified, distorted, and it's a beautiful image of exactly the phenomena that Einstein first predicted, gravitational lensing. But because we understand general relativity, we can actually work backwards and say what mass distribution would produce that lens. How much mass must there be there, and how must it be distributed? And so you can work backwards and invert the image, as it's called. And this is a picture of where the mass is. You see the little spikes where the galaxies are. But you notice that most of the mass in that system, by far the dominant mass in that system, is not in the galaxies, but between the galaxies, where there's no light. About 50 times as much mass in this system is contained in the stuff that doesn't shine compared to the stuff that shines. Now, this is one unshining example of what's become known, because physicists are very linguistically challenged. This is called dark matter. And in fact, what we've discovered is, in fact, not only is the dominant stuff of clusters of galaxies dark, invisible, not stars, not anything we can see with telescopes, but in fact the dominant stuff in our own galaxy is dark matter. And it's a fascinating subject because, in fact, there's so much of it that we have reasonable certainty, for reasons I really can't go into right now, that dark matter is not made of the same stuff as you and I. It's made of something else. It's made of some new type of elementary particle. And what makes that exciting is that means it's not just out there, it's in this room as you're nodding off during this lecture. It's going right through your body. And that means we can do experiments here on Earth. In fact, they're underground experiments to look for it. And in fact, maybe discover the identity of this dark matter, which dominates by a factor of almost 50 compared to all the stuff in all the stars and planets and aliens and everything we can see. A new type of elementary particle. So, in fact, the first lesson here is that you were even more insignificant than you thought you were before you walked in. But the important thing is we can actually now weigh the universe by finding out how much dark matter there is. And we've done it. And here's the answer. Now, whenever physicists have an important number, they always give it a Greek letter. And so we call it omega. And omega tells us how much matter there is compared to the amount of matter you'd need to make the universe flat, just the boundary between open and closed. And we now see from measurements like this and other ones that, again, I don't have time to go into, that to really great certainty, there's a factor of 3 too little matter to make the universe closed, or to even make the universe flat. This number is about 30%, so the total amount of mass in the universe in these clusters of galaxies is about 30% of what you need to make a flat universe, therefore suggesting that we finally answered this holy grail. We know the answer. We live in an open universe. Okay? Now, there's a problem with this. That is that theorists like me knew the answer. We always know the answer. We're not always right, but we know the answer. And we knew that we lived in a flat universe. And that's because a flat universe is the only mathematically beautiful universe, in fact. Actually, it's a little more subtle. I can explain it. I wouldn't normally do it, but I will in this crowd, I guess. So it turns out that what makes a flat universe so neat is that the total energy of a flat universe is precisely 0. That's why a flat universe is so beautiful. Because what makes 0 so beautiful? Well, if you want a universe to come from nothing, then 0 total energy is a pretty good value. Okay, so that was one of the many prejudices we had, but these damn observers kept coming up with the wrong number. Now, the point is that this is so disturbing by weighing these clusters that you might say, well, it's a very indirect way to determine the geometry of the universe. You weigh all the stuff and there's big uncertainties, and then you apply it to Einstein's equations and you work out the geometry of the universe. Wouldn't it be better to measure the geometry of the universe directly? Right? And the answer is, well, we can now do that. Again, I would never have thought 25 years ago that we could, although actually, remember, I actually ended up writing a paper about it, but I forgot about that. But how would you measure the geometry of the universe directly? Well, here's a simpler question. How would you measure the curvature of the Earth if you couldn't go in a spaceship, go and look down at the Earth, or you couldn't go around it? Okay. Well, the answer is very simple. You draw a triangle, and then you ask a European high school student, what's the sum of the angles in a triangle? And then they, okay, like Canadian high school student, and what's the sum of the angles in a triangle? And they'll tell you it's 180 degrees. You say, okay, but that's because you've learned your geometry from Euclid. On a curved surface, it's very different. If I take the surface of the Earth, for example, I can draw a triangle that's very different. I could draw a triangle by drawing a line along the equator and then making a right angle going up to the North Pole, and then another right angle coming back down to the equator, and that's a triangle with 3 right angles. 3 times 90 is 270. So if I drew a large enough triangle on the surface of the Earth, I could prove it was curved, because it wouldn't be 180 degrees. Now, it turns out remarkably that precisely the same is true for a curved 3-dimensional universe. If I could draw a large enough triangle, I could determine the curvature of the universe. And in the last decade, we've been able to draw a large enough triangle. And it comes from the most important observation in cosmology, perhaps, modern cosmology, the cosmic microwave background radiation, the afterglow of the Big Bang. And in fact, I remember I was reading out there something that's very neat, and I'm glad it's part of the International Year of Astronomy that you're promoting here. Because many of you have seen this radiation. It was discovered, this radiation from the Big Bang was discovered by accident in New Jersey, of all places, in 1965. But many of you have seen it, especially the older people in the audience in the days before cable television. Because in those days, the TV stations actually went off the air. And when they did, there's static on the TV screen. And if you look at the static, 1% or so of that static on a TV screen is the radiation coming from the Big Bang. So you've actually all seen it. Now, so let me just give you a little tutorial on where it comes from. So if we have a telescope here looking out, we're looking at galaxies that might be 1 billion light years away. So that means we're looking at them as they looked 1 billion years ago. Far, far away, long, long ago. Okay? And that means ones that are 2 billion light years away, 2 billion years ago. Well, if the universe is 13.7 billion years old, you'd think that if I looked far enough, I would see the Big Bang. And in principle, that's true, you could. But we can't, because between us and the Big Bang, there's a wall. Not a physical wall like this so much, but essentially it might as well be. I can't see outside this room because the wall's opaque. If I look out at the universe, I look back in time. And the universe has been expanding, so it's been cooling. So it was hotter back then, it was hotter, hotter, and hotter. And at a certain time, when it was 100,000 years old, the temperature of the universe was 3,000 degrees above absolute zero. 3,000 degrees Kelvin. At that temperature, the radiation is hot enough that the dominant stuff in the universe, which is hydrogen, gets broken apart by radiation. Every time a hydrogen atom tries to form, the radiation breaks it apart. So you don't have neutral matter anymore. You have what's called a plasma. The charges are separated. And a plasma is opaque to radiation. You can't see through a plasma. So if we look out, we can't see past this point. In fact, on the other hand, if we run the flow forward, the universe is opaque, 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 but then it cools down to the point where neutral matter can form, and then the universe becomes transparent. And just like this room again, I see that wall because the light from those lights gets absorbed by the atoms on that surface of that wall, gets re-emitted, and the air is transparent, and so I can see all the way to the wall. Similarly, for the universe, I can now expect to see, if there was a Big Bang, radiation coming at me from all directions from this so-called last scattering surface, the point where the universe became neutral, if you wish. So that's a signature of the Big Bang, and that radiation has been cooling down from that time to the present time. It should be about 3 degrees above absolute zero, and that's what was measured, as I say, by these guys in New Jersey who didn't know what the heck they were doing, but they won the Nobel Prize anyway. In fact, 2 Nobel Prizes have been given for this because it's so important. Because if we can measure this stuff, if we can get a picture of it, we get a picture of what the universe looked like when it was a baby. Okay? And I'll show you a picture of that in a moment. But for our purposes on that picture, there's one important scale. 1 degree. Why 1 degree? Well, this distance, represented by 1 degree here, is a distance of 100,000 light years. What's special about that? Well, the universe was about 100,000 years old, and Einstein tells us that no information can propagate faster than the speed of light. So that means anything that happened over here, this is how far a light ray can go in 100,000 years. So nothing that happened over here can affect anything that happened over here. So what does that mean? Well, if I have a lump of matter that's this big, Well, it knows it's a lump and it starts to collapse due to gravity and it heats up and all sorts of things happen. But if I have a lump that's this big across, it doesn't even know it's a lump. It's kind of like Wile E. Coyote in those cartoons where he goes off the cliff and waits a while before he falls. And in this case, gravity can't even travel across the lump because gravity propagates at the speed of light. So the largest lumps that can have collapsed significantly at that time would be about 1 degree across. That's the triangle we need, as you'll see. Because now I have a triangle, I have a ruler that's 100,000 light years across on one side, a known distance away from me. And in a flat universe, light rays go in straight lines. So the angle subtended by that ruler, that distance away, 100,000 light years across, the angle on my eye will be 1 degree that I'd expect to see. But in an open universe, light rays diverge as I go back in time. So the same ruler will subtend a smaller angle on my eye. It'll look smaller, maybe half a degree. In a closed universe, light rays converge as I go back in time. So the ruler will look bigger, maybe 2 degrees. So all I have to do is take a picture of that cosmic microwave background radiation and ask how big are the lumps. Are they half a degree, 1 degree, or 2 degrees on average? And I'll determine the geometry of the universe. And that's what was possible. The first real experiment that was able to do this significantly was this one. It was an experiment called Boomerang. It's in the South Pole, near the South Pole in Antarctica. It's a balloon and a microwave radiometer. It goes way above the Earth's surface because the Earth is hot. You're looking at something that's 3 degrees above absolute zero. And this experiment was designed to look out and measure a small region of the sky in microwaves and look for those lumps. And to do it, it went around the world, okay, which is actually easy to do in Antarctica. You can, if you're right at the South Pole, it's really easy. You just go this, like this. But over here, a little harder, but it took about 2 weeks for it to go in a circle, why it was called Boomerang. It looked at that region of the sky, and here's one of the images it took. This is we've superimposed the image on the original one. It reminds me of, just to mention, our cosmic myopia also. We can see visible light, but if we evolved to see microwave radiation, every day when we weren't looking at the sun, we'd be looking out 14 billion light years back and be looking at that microwave background surface. These are the hot spots and cold spots that correspond to lumps of matter and energy. And these are the lumps, and the question is, how big are they? And this is a different false color image of these lumps. This is the region of the sky seen in the Boomerang. And what we can do is we create a universe on a computer. And we can create a closed universe, an open universe, and a flat universe, and we can compare the size of the lumps we'd expect in each universe with what we see. And in a closed universe, the lumps, on average lump size would be about this big. But this is bigger than what we see. In an open universe, I don't know if the resolution of this projector is good enough, the average lump size is about this big. Okay? And that's smaller than what we see. But just like Goldilocks, in a flat universe, it's exactly right. In fact, we now know to a high accuracy that the universe is flat, that the lumps are exactly right. In fact, I think better than the Boomerang was an all-sky satellite that was sent up called the Wilkinson Microwave Anisotropy Probe in honor of David Wilkinson, who's one of the people who should have won the Nobel Prize for the first observation, but he and his colleagues were too polite. But this probe looked at the entire sky and looked at these lumps and, in fact, was able to, this is just to blind you with science, this is to show you all that really matters here, is this is the data, the points, and the predictions for a flat universe are right here. And you see most of the lumps, this is counting lumps, basically, as a function of size, and most of the lumps, the biggest lumps, are 1 degree across. So this tells us to high accuracy, to about 1% accuracy, that the universe is flat. Now, of course, if you've been awake for the last few minutes, I proved a few minutes ago the universe was open. So the question is, what's up? I already weighed all the stuff around clusters, and it was 30% of what we needed. There's 70% missing. Where could I hide the 70% of the stuff? Well, if empty space had energy, remember what it would produce. It would produce a cosmological constant, a la Einstein. And if there was enough of it, because it produces a repulsive force, the expansion of the universe, instead of slowing down over time, would speed up. So I measure the distance of objects as a function of velocity. Instead of seeing the kind of universe everyone had expected, I would see this. Well, in 1998, the world was stunned by a few groups that actually measured the expansion rate of the universe. Here's distance versus velocity as a function. And the question is, do these curves turn up or turn down? And to get a better idea of this, you can draw a straight line through this and make the whole thing down here, sort of drag it all down so this is horizontal. And the question is, do these faraway objects fall on this curve or this curve? And it's pretty obvious. They don't fall along the curve where the universe is slowing down, which is what everyone expected because gravity sucks. And just for fun, if I want to fit the data and say, let's say I put energy in empty space, how much energy would I need to fit the data to make the universe accelerate just by this amount? And the answer is, you need just what's missing. If you put 70% of the energy of the universe in empty space, you get exactly what we see. And that's exactly the amount that was needed. So we now have this cockamamie universe, and this is the universe we appear to live in, whose dominant energy is not dark matter. It's an energy in empty space, other kind of energy you can't see, which has been called, of course, dark energy. See how good we are? We can name things. Now, the question is, what the hell is it? And the answer is, we don't know. Now, it's not so crazy that empty space has energy, because in fact, in the particle physics world, empty space isn't so empty. Empty space is a boiling, bubbling brew of virtual particles that pop in and out of existence in a time so short that you can't see them. And in fact, I think, this is actually from the Nobel Prize ceremonies a few years ago. This is a picture of empty space inside of a proton. This is an animation, but it's a real mathematical calculation. This is what the empty space inside of a proton looks like. Fields that pop in and out of existence in short times. And in fact, we know that these fields are responsible for the mass of the proton. Not the quarks that make up the proton. They don't responsible for the mass. It's this empty space, the fields in empty space. So most of the mass of your body is due to this stuff. And we get the right answer for the energy mass of protons and elementary particles. Again, something fairly recent. So we have great confidence that empty space isn't so empty. So therefore, we should be able to calculate the energy of empty space. And when we do, we're a little embarrassed. Because we come up with the following prediction. The energy of empty space should be roughly a gazillion times the energy of everything we see. That is the worst prediction in all of physics. Okay? Probably. I don't know if Ray made any worse ones. We predict that the energy of empty space should be roughly 120 orders of magnitude larger than the energy of everything we see. And that's a problem. In fact, it's so big a problem that we thought we knew the answer when I was a graduate student. We just said, well, make it zero. And we were able to go to sleep at night. We were sure the energy of empty space was zero, but we now know it's not. It's an absurdly small amount compared to this. It's 120 orders of magnitude smaller than our prediction, but not zero. And we don't have the slightest reason or understanding why. It is the biggest mystery in physics. If anyone comes out to hear you and says they understand why, they're lying, especially if they're a string theorist, okay? We think its existence is probably tied to the beginning of the universe, and the key thing is it will determine our future. And that's what I want to spend the next few minutes talking about, how our picture of the future has changed because of our understanding that the dominant stuff in the universe is nothing. And by the way, this makes us even more insignificant than we were 15 minutes ago, right? Because before we were relatively insignificant compared to dark matter, but now us and everything we see is less than 1% of the total energy of the universe. We really are just a little bit of pollution, okay? Now, so I'm quoting various philosophers here, and so this one is I'm a big baseball fan, and the future isn't what it used to be because of this. So let me describe some of the reasons why our future is so miserable, and then I'll come back to something. Yeah. The first person to realize our future is miserable in a number of ways was George Orwell, with books he wrote, but he also said, to see what is in front of one's nose requires a constant struggle. Okay? And of course, this is what he meant by it. What this tells us, and what he knew, is that in fact, in a universe that's dominated by the energy of empty space, that energy is gravitationally repulsive. And if it's a constant, what it means is our universe will expand exponentially. That's what that mathematics there says. But more importantly, it says the velocity of objects, and this is the way we write velocity, is proportional to the distance of objects away from us. The farther objects are away from us, the faster their speed. Okay, fine. But the constant of proportionality is a constant for all time if the energy of empty space is constant. And that means that this number eventually gets bigger than the speed of light. Objects greater than some distance d away from us are now receding from us faster than the speed of light. Now, that's not allowed, right? Well, that's because we lied. Okay? In school we say you can't travel faster than the speed of light, but you have to be like a lawyer and parse it a little more carefully. Okay? Nothing can travel through space faster than the speed of light, but space can do whatever the hell it wants, as far as we know in general relativity. And so space can carry objects away faster than the speed of light. In fact, objects can be standing still and still be moving at the speed of light. You're doing it right now, depending upon how much coffee you had before the lecture. We're not moving very fast at all with respect to the sun, but with respect to an audience trapped in a room in a galaxy in the other end of the visible universe, we're moving away at the speed of light. And that audience is not moving fast relative to their surroundings, but they're moving away from us at the speed of light. How can that be? Well, they're at rest and we're at rest, but the space between us is expanding. And so in this case, what this tells us is that objects that are further and further away from us are eventually going faster and faster and faster, and eventually, in fact, will go faster away from us than the speed of light. Space will carry them away faster than the speed of light, and that means we won't be able to see them, because the light won't be able to make it back through space to get to us. We can ask what that distance d is, and if we plug in the energy density in some absurd units of empty space, we find out that that distance is about 18 billion light years. Now the universe is about 14 billion years old, so this is becoming visible now. This effect is becoming visible. So what will it imply for the future? Okay. Well, what will happen? In astronomy, we talk about redshifts. See, when objects move closer and closer to the speed of light, they won't just disappear. As they get closer to the speed of light, the light from those objects gets stretched, gets redder and redder and redder. That's called redshift. And in fact, if you get to the speed of light, the redshift is infinite. So instead of just disappearing, those objects will get redder and redder and redder and dimmer and dimmer and dimmer until they go sort of twinkle out. And we can ask about the redshift of these objects. And it turns out, if we ask how big is the size of the largest region we can see in the universe that's traveling less than the speed of light away from us, compared to the size of the biggest bound object, our local supercluster. Because one of the biggest misconceptions about the expanding universe is that everything's expanding. Okay, it's not. I mean, well, some of us are expanding, but the Earth isn't expanding because it's gravitationally bound. The solar system isn't expanding because it's gravitationally bound. Our galaxy isn't expanding because it's gravitationally bound. The only things that are moving away from us are those things that are not gravitationally bound to us. So if we take the largest bound object we're inside of, maybe our local supercluster, and take the ratio of its size compared to the size of what is the principal visible universe, it's a factor of 5,000. If we plug in an exponentially expanding universe to that, we can do some calculations. And here's what we find. In merely 150 billion years, which may seem like a long time to some of you, although not long compared to this lecture, it's not long at all. It's really, in fact, in 150 billion years, the universe will look essentially the same. Main sequence stars like our sun will still be burning. There'll be planets that can be around those stars, powered by solar power with elements like our own, so there'll be astronomers and all the rest. But in 150 billion years, the redshift of every object outside of our local supercluster will be at least 5,000. That means the light will be shifted by a factor of 5,000 into the red and infrared, etc. But that won't make them invisible because there's lots of high-frequency radiation. There's X-rays and gamma rays and all the rest, and that'll be shifted into the visible. So they won't be visible yet. But the great thing about an exponential is it's an exponential. So in merely 2 trillion years, which again is short compared to the lifetime of the longest main sequence stars, the redshift of all objects outside of our local supercluster will exceed 10 to the 53. What does that mean? That means even the highest energy cosmic rays that we now measure today, the highest energy cosmic rays with these big detectors we have, in this case in South America, their wavelength will be redshifted so large that their wavelength will be larger than the size of the observable universe. And that means they're not visible. That means every bit of radiation coming at us from everything outside of our local supercluster will now be invisible. The rest of the universe will have disappeared. Now, I'm an optimist, as it should be clear, and I've tried to turn this into something useful. So I've argued in my country at Congress now, that we should fund cosmology now while we have a chance. There's a problem, however, and that is that there's an impedance match, as we say in physics, mismatch. The long-term future for a congressperson is 2 years, not 2 trillion years, so this doesn't matter. So I haven't been able to convince anyone. But the future is such that the universe will disappear. Okay? Now, so the long-term future is miserable, but I want to show you the short-term future may be miserable. This is already confronting science with problems that are so great that it may end science as we know it. So here's a problem. This is a picture that has driven many physicists mad. I'll explain it. This is a brief history of time, if you want. This is the density of all the stuff in the universe as a function of time. This is the density of matter in the universe. It goes down as the universe expands. Density of the universe decreases as the universe expands. But empty space, the energy of empty space, if that's what it is, remains constant over all time. So in this picture, we happen to live right here, when the energy of empty space is about a factor of 3 bigger than the energy of all matter in the universe, including dark matter. But there's something weird about that picture. This is the only time in the history of the universe when these two numbers are about the same. At all early times, the density of matter was much greater than the density of empty space, the energy density. At all late times, the energy density of empty space will be much greater than the energy density of matter. We appear to live at the only time in the history of the universe when these two numbers are about the same. And this is crazy because the whole idea is we don't live in any particularly special time in the universe. Why should 14 billion years after the Big Bang these two numbers be the same when we happen to be around? This is nuts. So some people have come up with an idea for maybe how to explain it. There's that picture. And so to explain it, they look at this picture. And they say there's something in this picture. Galaxies. Maybe that explains why we live when we live. Why? Well, let me just try and show you. Here's the energy of empty space we measure today. But let's imagine that the energy of empty space were slightly larger, say 50 times larger. Then those two curves would cross at that time, right? Well, when's this time? This time is when galaxies first formed. So if the energy of empty space was greater than this, it would dominate over the energy of matter at the time galaxies first formed. But the energy of empty space is gravitationally repulsive. So if it dominated over the energy of matter, galaxies would never have formed. The repulsion would have beat out the attraction. There'd be no galaxies. Maybe this is telling us something. Because if there are no galaxies, then there are no stars. If there are no stars, there are no planets. If there are no planets, there are no astronomers. So some people have argued that maybe that is the explanation. That if, in fact, let's say there are many different universes, and in each different universe, the energy of empty space is a different number, just a random variable. That only in those, when it's not much greater than what we measure, will galaxies form, and then stars and planets and astronomers. So the universe is the way it is because there are astronomers in it today. It sounds stupid. It may be stupid, but it may be true. And so I do want to come back to Einstein again, because he asked, although in the incorrect way, said the most interesting question to him was whether God, and by God he didn't mean God, had any choice in the creation of the universe. What he meant by this was, are the laws of physics consistent if we changed one thing, or is there only one possible universe that could exist? And if I changed one little bit, the whole thing would come apart. He wanted to know if nature was unique, if there's only one physics. And this is really asking the same question. Because if there are many different universes and they have different laws of physics and different energy of empty space, then nature isn't unique in some sense. So this is a fundamental question that people are asking now. But worse, particle physicists have begun to ask the question. And particle physicists said, you know what? We're way ahead of everybody else. This is just one number that the astronomers don't understand. We in particle physicists have not understood much more for much longer. And they say, okay, look, there's a lot of things we don't understand. Why is gravity the weakest force in nature? Why is proton 2,000 times heavier than the electron? Why are there 3 generations of elementary particles? Who ordered them? Okay? A whole slew of things. So the particle physicists, some of them said, hey, this is great. You know, maybe we don't have to explain anything. Maybe everything's an environmental parameter. Maybe there's no fundamental quantities. Maybe everything is an environmental accident. And then what you need is not a theory of everything, but rather a theory of anything. And we have such a theory. It's called string theory. So I have a slide here, a brief summary of string theory for those of you who may not know about it. This one guy says to another, I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. And the second person says, okay, what would that imply? And the first person says, I don't know. Okay, so that's the story of string theory for the last 30 years, in fact, because it hasn't explained anything. But in fact, it has produced something. And that is this recognition that string theory requires there to be at least 10 or maybe 11 dimensions in nature, most of which we don't see. But if that's true, since we live in a universe with 3 dimensions, and the rest of those dimensions, something must happen to them. And the conventional argument is that they get curled up into regions so small you can't see them. But for every different way of curling up those extra dimensions, you come up with different laws of physics. And so, in fact, string theory provides what's now become called a landscape. Here's a picture of all these extra dimensions curled up in each different way. You end up with each different point in this picture is a different 3-dimensional universe with different laws of physics. And in each universe, maybe the energy of empty space is different, and maybe we live in the valley because that's the right place to be. So string theory does provide that landscape. The question is that the picture of nature? And we don't know. You might ask, of course, if it's really science at all. Because some people have argued that there are possibly 10 to the 500 different possible universes, types of universe that could be the basis of string theory. That means basically it would be consistent with anything you could ever measure. Because somewhere there's a universe with those properties. But if you're consistent with anything you could ever measure, that's not a scientific theory. Because in order to be a scientific theory, you have to be able to falsify it. But if there's nothing you can do to falsify it, it's not science. It's even worse because in order to predict why we might be living here, you have to use probabilities over all of these universes. And there's a big problem with probabilities. I think I drew one of the big problems right there. Namely, that the predictions you make for the universe depend upon what you assume is in the universe. So if you assume that you have a universe that has to result in George Bush, God forbid, then you'll come up with very different predictions for the laws of nature than if you predict a universe that doesn't have him, which would be a better one. Okay, so that's a problem. And that's a big debate in science nowadays, and it may change and end the way we think about fundamental physics. In the future, and I'm talking about the very far future, what will astronomers and physicists in the far future on some different galaxy, again, long in the future, far, far away, what will they determine? Well, they'll come up with the same laws of physics we come up with because those laws work. They'll discover electromagnetism and quantum mechanics and all the things we've discovered. They'll build telescopes and they'll look out at the universe and they'll come up with completely the wrong answer. They'll even discover general relativity. But when they look out at the universe with the best equipment they can come up with, they'll come up with the wrong answer because the Big Bang will have disappeared. All evidence for the Big Bang will have disappeared. In fact, they'll come up with the picture that de Sitter had and Einstein had at the turn of the last century. This is our own universe. It's a galaxy. It's not our galaxy. Why? Okay, I want to see if you're still awake. We live in our galaxy. It's the Andromeda galaxy, but it doesn't matter. Once you've seen one, you've seen them all, more or less. Sorry for the astronomers in the room. But in the far future, that's all we'll have. Because remember, and I'll just rush through this quickly, basically all evidence for the Big Bang will disappear. All of the fundamental building blocks of the Big Bang that now tell us it really happened will have gone away. The Hubble expansion, the thing that Hubble discovered in 1929, will have disappeared. Why? Because he saw galaxies moving away from us. But in the far future, there won't be any galaxies moving away from us because all the galaxies will have disappeared. So all the galaxies we could use to trace the Hubble expansion will have gone away. Now, in fact, this has a profound implication. There'll be no evidence for dark energy. Because even though in the far future, the density of matter will have gone way down and the dark energy will really be dominant, we won't be able to see it. When the universe is 1 trillion years old, the density of matter compared to the density of dark energy will be 1 part in a million, meaning matter will be insignificant compared to dark energy. But we won't have any evidence that dark energy exists. Because how do we know dark energy exists? By measuring the acceleration of the universe. But there are no probes to measure the acceleration of the universe. In fact, the only time when you could measure dark energy is right now. When the dark energy density is much smaller than the energy of matter, you can't measure it because it doesn't affect the expansion of the universe. When it's much greater, it's already forced everything to go outside of the horizon and become invisible, so you can't observe it then. Now is the only time we could know dark energy exists. But you say, wait, what about that microwave background that I saw on my TV? Well, it goes away too, for a number of reasons. One, because it turns out as the universe expands, the frequency, the microwave radiation redshifts, and its intensity goes down. So when the universe is about a trillion years old, the intensity of the microwave background will be down by 12 orders of magnitude. Experimentalists will have to be 12 orders of magnitude smarter to find it. Well, that may not be difficult, but still, it turns out that that's not good enough. Because in fact, in our galaxy, there are free electrons. In fact, in our galaxy, there's a plasma. And when you have a plasma, it's opaque to radiation, I told you. It turns out it's always opaque to radiation smaller than some frequency given by what's called the plasma frequency. We can calculate that number. It's a kilohertz in our galaxy. And that means it turns out when the universe is 50 times its present age, the microwave background will have redshifted to the point that none of the radiation can actually make it into the galaxy. So even if you could build a great experiment, you won't see anything. There'll be no microwave background. Well, you get the idea. It turns out the other big pillar of the Big Bang is the so-called abundance of light elements. Most of the elements in your body, as also says in that little poster out in front, were not created in the Big Bang. They were created in stars. You're all star children. All the oxygen and iron and all the things that make you around was created inside the core of stars, which exploded so that you could be around today. But helium, deuterium, hydrogen, and a little bit of lithium. Lithium's not important. Well, it's maybe for some of the people in this room it's important, but it's not important in the universe. This is one of the great, I have this as a little pocket slide. Whenever someone tells me there wasn't a Big Bang, I say, look, there was a Big Bang. Because we can predict with the Big Bang what the abundance of these elements should be, because they're created in the Big Bang. And we get 25% of the universe is hydrogen, and roughly 1 part in 10 to the 10th is lithium. It all works perfectly. But stars make helium, okay? 25% of the universe is helium, not hydrogen. And all the helium essentially we see nowadays, almost all the helium in the universe was created in the Big Bang. But in 1 trillion years from now, it turns out stars will have created enough helium so that 60% of the mass of the universe will be in helium. The component coming from the Big Bang will also have disappeared. There'll be no evidence, there'll be no need for primordial helium production. Stars themselves would have been able to create all of the helium. So every bit of data and theory that you could apply would tell us, when you look out, that the observers in the future will live in an island universe, a single galaxy or metagalaxy, surrounded by an empty universe that isn't expanding, that's static and eternal. The same wrong picture we had 100 years ago. Now, we'll return poetically to that level of ignorance. So I want to end with the good news. The good news is that we live in a very special time. The only time when we can observationally verify that we live in a very special time. Now, what I mean by that is facetious, clearly. It's actually something rather profound. What it really means is that maybe it's true. Maybe that anthropic principle is actually true. Maybe there are no fundamental parameters in the universe and everything is environmental. And that really means that science at a fundamental level will change. So, or maybe even end. And so instead, in fact, I'll leave you with this, that we will be lonely and ignorant, but dominant. And I've been living in the United States for a long time, and I'm very used to that. Thank you very much. Thank you.